Okay guys, so now let's cover Lab 7 and 8. There's not a whole lot that you need to know for Lab 7. You need to know what sort of things affect a reaction rate. The biggest things that we talked about are temperature, concentration of reactants, and surface area. Other than that, there's not a whole lot that you need to know for Lab 7. That brings us to Lab 8, in which there are quite a few things that you need to know. Some people have a lot of problems with figuring out the order of a reaction, so I'm going to take you through one of those problems. Let's now move. Okay, so well, you need to understand that essentially the slower that a reaction is, that means that the rate is so the longer that a reaction takes, the lower the rate will be. So in other words, the rate is inversely proportional to the amount of time that it takes for this reaction to come to completion. You need to understand that the order of a reaction is essentially the sum of m and n in this equation. So if you have like for example K times the concentration of A to the third times the concentration of B to the second, that will be a fifth order reaction. Now, in terms of the actual math, we won't be doing anything above first or second order, but you do need to understand that what the integrated rate laws will give you. And so, for a first order reaction, and that's given right here, the first order reaction is given by the ln of the concentration after time t is equal to negative Ka times t plus the ln of A. Now I've drawn a little graph for you right here that looks kind of like this. So the intercept, that point right there that I'm moving around, that is going to be ln of your initial concentration of A. That will essentially be, if we turn this into y equals mx plus b, that is your b or your intercept. Now this Ka right here, that is going to be your slope. So for example, if you have a very small slope, your line might look like this. If you have a very high slope, your line will look more like this or like this. And finally, that's going to be like m in your y equals mx plus b problem. And finally, the last part is the t, and that is going to be kind of like your x variable. So just to reiterate, y, or ln of A of t, is equal to m, or negative Ka, times x, or t, plus b, or ln of your initial concentration of A. So that's for first order reaction. You also need to be familiar with your second order reaction, which is essentially very similar, but now we have 1 over A and we have a positive Ka value. Okay, so let's go through an example problem. Let's say you're going to be given a graph of rates. So we're going to say that our initial concentration of A is this, and we're going to have a few different ones, and your initial concentration of B, and you're going to be given a rate. So from this information, you are going to be able to calculate what your equation looks like. So let's say we have an initial of 0.2, then we have 0.3, and remember this is all in molar, but I will not write that in order to just save a little bit of space. Okay, and for B we have 0.2 almost all the way through, except for the last one, which is 0.4. And now our rates, now remember that these are not going to be perfect ratios. We're going to have kind of a rough ratio, but it will be pretty close to what we're looking for. So if we have a graph like this, how are we going to figure out whether we have a first, second, or higher order reaction? So to do that, what we're going to have to do is we're going to have to keep a variable constant. So let's go ahead and use this guy right here, and this guy right here. And now the reason I've chosen that, no particular reason, but one of these does have to stay constant. So in this case, B is constant at 0.2. Now how has A changed? Well, A doubled. So A increased by twofold. And what happened to our rate? So to figure that out, we can go ahead and divide our rates. So we had an increase of twofold, and then if we take 1.71 times 10 to the negative second divided by 4.28 times 10 to the negative third, we get 3.99, which I'm going to round to 4 times more. Now, what does this mean? This means that we can think of this as a ratio. So because we doubled this guy right here, so 2, and we did 2 to the what power for this guy? So that's 2 to the second power. Now, that tells us that we have a second order based on A. So let's go ahead, and over here we're going to write our equation for the rate. Rate equals K times the concentration of A to the what power? Well, this is going to be our first power, second power, because we changed A by doubling it, and our rate quadrupled essentially. Okay, now let's go ahead and figure out what is the power of B. So to do that, we're going to do a similar thing, but now we are going to look at the concentration of, we're going to have to hold the concentration of A constant. So I'm going to use these two and these two. So notice again, we hold A constant, we doubled B, and what happened to our ratio of the rates? These actually, I'm not going to go, you just take 3.32 and divide it by 1.71, and that is also doubled. So since these have both doubled, we say 2, and I'm sorry, this is not obviously equal to 2, but it's 2 to the second power. That's the important part. So we doubled here, and this is going to be equal to 2 to the, well, not equal to it, but it's going to tell us how our rate changed over here. So our rate increased by 2 as well, so that's 2 to the first power because it did not quadruple, it just doubled, which tells us that the power of B is 1. Now that tells us we have a third order reaction, and that this is our equation so far. Okay, so now let's finish this problem. Let's figure out what is K. So in order to find K, we can just pretty much use any of these data points. So, well, we've kind of run out of space, but I'm going to see if I can squeeze this in. So I'm going to just use any one line. So I'm going to choose this line to use. And so I'm going to do rate, which is 4.28 times 10 to the negative third, is equal to K times the concentration of A, which is 0.2 squared, times the concentration of B, which is 0.2, 0.2, to the first power. I know that's really kind of squeezed into the corner, but hopefully you followed what I was just doing. So that's going to give us a K value. Well, we're going to have to then solve for this, so I'm just going to go ahead and clear this and redraw it. So we have 4.28 times 10 to the negative third is equal to K times the concentration of A squared times the concentration of B. So then we just go ahead and divide by A squared times B, and that will find us our K value, which I get 0.35 or 0.535. Done. Next lab. Okay, and I just wanted to clarify, to spend a little more time clarifying how those numbers came about. So I'm going to do another example with those same numbers, but now we're going to use a different concentration of A, a different change in concentration. So remember, once again, we have to hold one of them constant, so we're going to hold B constant while we change A. So now, what is this multiplication? If we divide zero point 0.3 by 0.2, we get 1.5. So that has increased by 1.5. And by how much has this increased? So to do that, we just take that same 9.56 and divide it by the 4.28, and we get 2.23. Now, you might want to push that down to 2, but you don't want to do that. And the reason is because 1.5 and 2.23 are not exactly real close to be first order. So this 1.5 tells us that we're going to use a 1.5 base. So 1.5 to the what power is equal to this guy, which is 2.23. So that's going to be a second order. So if we take 1.5 and square it, we get essentially 2.25, which is very, very close to 2.23. Now, in the previous problem, what I did was I did 2 to 4, so that was a 2 times. So our base here was 2 to the what power, and then this increase in rate, blah, 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 whatever these concentrations were, that was a fourfold increase. So 2 to the what power has to be equal to 4. So that will tell us our concentration of, or our power exponent of A. So that tells us, since it has to be equal to 4, the only way to do that is to put a 2 in there. So 2 to the second power is 4, and we also have 2 to the second, or 1.5 to the second power is 2.25. So A is going to be a second order rate. So R is equal to K A to the second power times B. So I just wanted to clarify that. Alright, on to Lab 9.